Okay, so let's talk about our fourth unit. The fourth unit, like I said, for lack of a better word, it's kind of a physics-based unit. Um, but we're going to be talking about electricity and energy and how to understand the basic properties behind how electrical devices work. And in doing that, there is a there's a large number of questions that involve some math. So if you want to use your cell phone, that's probably fine. But I might recommend, if you have a calculator, because are you guys doing math this semester? Okay. If you have a calculator, maybe bring it. If you don't have a calculator, I can live with you using your cell phone. Like, I'll trust that you're not cheating on tests. But you may want to bring a calculator, just because we're going to do a decent amount of calculations, as you can kind of imagine, because if you're doing some sort of like engineering work or electrical work, you've got to calculate a few things. So now, we're not going to get to that today, though, so you don't really need your cell phones for that. So if you guys are on your phones following along on notes, that's fine. But if you're just on your phones, just being on your phones, maybe put them away. So let's talk about energy then. Physics is really the study of energy and matter. And I want to begin with that. Do you guys remember the word matter from our chemistry unit? What is matter? Check. Anything that takes up space, which means it has a volume. But there's one more thing to it. It has space or volume. Serena? Yeah, it has to have mass, which means it has to weigh something. That's the requirement for something to be considered matter. Basically, matter, like we've said before, is our stuff, right? If it's something that you can see and touch and throw, it's probably matter. But energy is a bit different. For example, energy would be something like light. Light is a form of energy, or fire giving off heat and light would be like a form of energy. And maybe you can touch it sometimes, maybe you can't. Like, for example, the light right here, weigh the light on a scale. How much does this light weigh? Well, it doesn't weigh anything. It's light, right? So, but it's energy. I mean, it still takes up space. Clearly the light is filling up the room. It takes up space, but it's not matter. So we're going to focus more in this unit on energy. Very specifically towards the end of today's lesson and starting tomorrow, we're going to talk about the form of energy known as electricity. And my personal opinion is that electricity, the discovery and how to create electricity, has got to be one of the most important, achievements that humans have ever come across. Like, when you kind of think about it for a bit, we take it for granted now in the 21st century, things like, well, the cell phones you have in front of you, and the lights that we have, and the heat that we get from our furnace. But like, if we were to go back only 100 years, I mean, first of all, cell phone devices not even close to invented yet. The light bulb, yeah, the light bulb was invented, but constant sources of electricity hadn't been figured out. You might have heated your house by a single wood-burning stove, and you might have needed to use candles for light. And like I said, we're not talking that long ago. We're talking maybe 100 years ago that would have been a reality. The fact that we can now consistently create electricity and create these devices that you guys are all looking at right now, like that's pretty incredible, right? So before I get to that, though, let's talk some more about the idea, like big picture, what physics is. Okay, physics is about how energy and matter work with each other, and it really, we call it the study of natural phenomena. That's actually where the word came from. It came from the ancient Greek for nature. Things in nature, people wanted to explain, well, how do they move? Why do they go where they go? For example, if I were to take this pen right here and let go of it, what do you think is going to happen? Why? Right, and we now know about that because someone repeatedly did experiments over and over and over again. But then someone might want to ask the question, well, there's this pen, which kind of fell, and then there's this piece of paper. The piece of paper did fall, but did it fall in the exact same way? And then people eventually started to realize, well, maybe there's things like air resistance. Maybe there's lift due to air particles causing the paper to float. Now, I don't even have one in the classroom, but imagine that I had a balloon filled with helium. Would that fall to the ground? But now that asks the question, well, why did that occur? Because gravity should still affect a helium balloon. And then people started to realize things about density and how helium is actually less dense than air. And what was happening is gravity was still occurring, except gravity was pulling the air molecules down. We can't even see the air molecules, but air molecules are getting pulled down by gravity. and that would cause the helium balloon to get moved up on top. Right? And so that's what physics tries to discuss, is like, how do these things that are like in nature, how does the universe behave? That's what I have written here. That's what physicists try to figure out. So there's a lot of correlations with chemistry. There's a lot of correlations with math, and especially astronomy. A lot of physicists want to try to figure out, well, why does the Earth rotate? Why does the Earth go around the sun? What is out there in outer space? Which is why I think it's cool that this unit is going to back end onto the space unit. So I think I'll leave that there. You guys don't really need to memorize this for a test, but I want to just begin with that as my intro as to what physics is. I want to then talk a bit about some history in terms of physics concepts. And they might not even called it physics at the time. I want to refer to a theory that existed basically over 2,000 years ago. We're talking 500 years BC. So, I mean, we've got 2,000 years AD. We're talking 500 years even before the birth of Christ. And there was a theory. They figured that all matter in the world was either going to be earth, air, fire, or water. That's what Aristotle thought. We talk about this at some point, the 4 elements in the chemistry unit. Right? And this theory they had was that everything was one of these 4, which was very, very wrong. Well, it was a great idea, but they would have thought that like a human was made of like some water and maybe some fire and some air maybe. And that like a tree was made out of some earth and some fire. And here's the really important thing. Some of these objects they thought contained fire because when they burned them, fire was released. So they figured that like trees have a lot of fire in them. And the fire is just waiting to escape. As soon as you get it going, the fire can finally like burst out of it. Well, nice idea, but like that is not how the world works. Eventually, they came across the same concept, but like they put a theory to it. They called it caloric. And I don't know that I discussed this with you guys already before. This might be new, I think. And so they put a word to it. They called it caloric, which basically was like their idea of heat. And they figured that there must be this heat, a substance inside of things, kind of like a liquid. And somehow this caloric liquid would like transfer from certain things. For example, imagine that you had a hot cup of coffee. The theory was that coffee has a lot of caloric in it. And the idea is that this caloric, this invisible, massless, like fluid or liquid, would escape. And you could feel it escaping because it felt hot. And so anything that felt hot must have caloric in it. And if it ran out of caloric, it felt cold. And so this magical substance, this massless substance, was like the thing that created heat. What is the problem with both of these theories is that they didn't understand the concept yet of energy. They thought that there was like an item, a physical matter property of fire. They thought that fire was a substance like matter. And they thought that this caloric was a substance like matter that somehow flowed. But like I said, we know better. We know about how there's mass and how opposed to mass there's forms of energy. And I want to relate to you guys a really important experiment that happened. This didn't happen until the 1780s. Up until this time, they really didn't know the difference between the two. This guy, his name was Count Rumsford, and he was observing a very common job at the time. It would have been a blacksmith. You guys know what a blacksmith kind of is? Or like they're working with tools, trying to forge and create things out of metal. For example, you could be a person who makes swords, or you could be a person who makes cannons. And that's actually the picture I have right here. So you've got these blacksmiths, and they're making a cannon. How do you make a cannon? Well, you take a drill bit, and you kind of find a way to rotate this drill bit inside the cannon, and it grinds a hole inside a big piece of metal. Now, here was where Count Rumsford came in. At the time, people thought that there was this magical, mystical caloric, this thing that like some things had heat, and it could somehow escape from you. So like, for example, a piece of wood must have had caloric, because if you lit the wood on fire, it could escape, and all of a sudden heat comes out of it. Right? And so here's what was weird to them, though. They had a piece of metal. is metal usually hot or cold? Usually metal is actually quite cold. And the drill bit was also cold originally. But you guys might already know this. What happens when you take a drill bit and you put it inside a cannon and you start grinding it? What happens to it? Friction causes it to get hot. And so this was weird to them because they could not figure out the source of the caloric because they had two materials that were both cold. And according to their theory, therefore had no caloric. And they ground them next to each other. And that friction, just like if you rub your hands together, you can feel it getting warm. They couldn't figure out, well, why is it getting hot? And so Count Rumsford had kind of the first recorded idea of energy. And they suggested, well, maybe there's not like an item, an actual tangible matter of caloric or of, like these guys thought it was fire back then. Maybe there's mechanical energy being converted to heat through the form of friction. And this really changed people's perspective. There's the word I'm looking for. It changed their perspective because rather than thinking of the entire universe as just being matter, they now realize that there's matter and energy. Now, this seems maybe a little odd to us because you guys have been born into a world where you recognize energy, right? Ever since you were a little kid, you probably understood how a light switch worked. Like my 1-year-old already kind of even understands how to use a tablet. You know, a little embarrassing that my 1-year-old knows how to use an iPad, but like they do, right? Like you guys have lived in the world where you know how light and heat and sound and electricity works. But you got to keep in mind, we're talking 300 years ago, they didn't have light bulbs. They didn't have electronics, right? The only sources of energy they really understood at that point was probably light, heat, and sound, probably coming from one place, fire. That's probably the only source of energy they really knew about. And now, all of a sudden, Count Rumsford discusses, well, what about friction? What about when we moved two things next to each other? All of a sudden it got hot. I didn't make something new, but I made energy out of it. Right? I want to show another picture kind of the exact same idea. Maybe a way they would have done this would have been to have horses rotating around in circles. This would have caused this little mechanism to rotate, which would cause this mechanism to rotate, which would cause the cannon to be ground out, and all of a sudden something cold became something hot. Do you guys get where I'm going with this, like what I'm saying on this? Okay. So with that historical context being added then, I want to talk now about our current theories of energy. So I mean, these are really only a couple of hundred years old. We now refer to energy in a few different ways. We sometimes refer to energy as having mental or physical stamina. For example, if you walked in this morning and you were a little tired and you're like, oh, 8 o'clock in the morning sucks, I need coffee. You might say, I have no energy. That's okay. Like, we use the word energy in different contexts. That's not really the scientific definition of energy. Now, you might say that, like, before you go play a basketball game, I need some energy, so I'm going to eat a protein bar. Again, we use that word, but that's really not the scientific definition of energy. Here's the definition of energy that we try to use. The best definition that we have is that it's a prerequisite for performing work. That's actually the definition that scientists give to energy, is that if you have energy, you can then do something. I don't know what that something is. That something could be anything. That something could be lighting up a room. That substance could be looking at something because you now have light. It could be heating something up. But like if you're able to do some sort of work, we often consider that energy. But energy, we've now learned, is a very broad term. There's a lot of different types of energy. And I'm going to fast forward in my notes, not to this slide, but I want to go to this slide right here if I could. So for those of you who do have notes printed off, fast forward a bit. I'm going to loop back again. I want to use this slide next. There are many different forms of energy that in the last 300 years we've kind of discovered. Let me talk about a few of them. We now give the definition thermal energy. But what does thermal energy kind of mean in people words? Anybody know what thermal energy means? Yeah, heat. Yeah, so this is one form of energy, heat. We've also learned about something called chemical energy. For example, there are chemicals that can give us energy. Most commonly, in, like, say, something like batteries, right? If you have a cell phone or a calculator or anything that runs on portable energy like a battery, we can store energy in a battery. Now, that's not the only place we store energy for chemicals. Where do you guys get the energy you need to be active? Your food. Also the sun, yeah, but indirectly the sun, but food, right? You guys hopefully are going to eat breakfast, or you have eaten breakfast, right? When you take food and water in, your body will convert that into chemical energy, and that gets stored inside your body in your muscles and fibers. And so that's another form of chemicals that give you energy. Now, we're all pretty aware, hopefully, of electricity. That is going to be the main focal point of this unit. We're going to mostly focus on electrical energy this unit. But before we get there, I'm going to spend at least half of this class discussing energy formats. What is a radiant energy? Radiant. What did you say? Glows? Close. That's going to be luminous energy. So let's hop ahead to that one. Luminous energy is something that glows or has light to it. So nice attempt. Anybody ever gone to the dentist and they needed to check your teeth, but they used like a special instrument where the hygienist probably even walked out of the room, they put a little thing up next to your teeth there, and an X-ray. Radiation. That's what we're talking about here. Radiant energy is like radiation. And there's a lot of different forms of radiation. Sorry, that didn't spell very nicely, right? X-rays are one form of radiation. Gamma radiation is another form. If you were to have like a nuclear bomb or a nuclear power plant, that involves eventually turning something into radiant energy. And one of the reasons why it turns into radiant energy is that there's also nuclear energy. Often these two things go hand in hand. Often nuclear energy causes radiation. We don't want it to, by the way, right? But it's an unfortunate side effect if you're not careful. There's also energy from magnets. You guys are probably pretty familiar with magnets. What about elastics, right? If I were to have a slingshot, for example, I were to put something in the slingshot and pull back. If I were to let go, it's going to go flinging forward, right? Like a bow and arrow, right? Even I used to do this with, like, I have a younger sister. I'd always take her little hair elastics and fling them at her, right? That's elastic energy. Sound. Sound's another form of energy. Here's one that you guys might not be as familiar with the terminology, but I'm sure you know the idea, just not the word. The word is mechanical energy. And the best way of me describing mechanical energy is to go back in pictures to this right here. Where did the energy to cause the grinding come from? Well, ultimately it came from the horses. And these horses were moving. And so anything that is like in motion and is moving around, the word we give to that is mechanical energy. Now, sometimes we think of mechanical energy as involving like machines, and that works too. Like if there's a machine that literally picks up this thing and moves it from there to there, that involves motion. But it doesn't even have to be a machine. It could be you or me. As I am moving around, I am doing mechanical energy now as I move things. Okay? So that's probably the best way of describing mechanical energy. The last one is one that you guys won't even learn until you get into grade 12. But has anybody ever seen this formula? It's very famous. It's Einstein's probably greatest achievement. E equals mc squared. Anybody ever seen that formula before? We don't use it in grade 9 or even in grade 10 or even in grade 11. I'm about to teach it to my grade 12 students in a couple weeks here. But this formula here is known as mass energy. And to kind of give you like the 30-second blurb, basically the way this works is that this m right here for mass, Einstein discovered that mass can be used to form energy. And basically, you know how I've been discussing how physics is the study about how energy and mass are related to each other? It's actually possible to turn matter, mass, into energy. That's actually possible. But like, I need to teach you guys a lot more stuff before we get there. So I kind of want to leave that there for now. But if you want to know more about Einstein's famous E equals mc squared equation, I can tell you more later. So anyways, the point I wanted to make on this slide is that we now know, over about the last 300 years of history, many different forms of energy. And some of them are alike, and some of them are related, but like they're all very different. You know, luminous energy is very different than mechanical energy, which is very different than nuclear energy. Right? However, nuclear and radiant often go together, or electrical and chemical often go together. For example, if you have a battery is often used to make electricity. Right? Or thermal energy and luminous energy often come together, because often when you get heat, it often glows or gives light. Okay? So now let me go back in a couple of slides here. The word energy then originally was from the Greek word energos, and it meant active. And originally it was describing things in motion. If things were moving, they had energy. Like I just described mechanical energy. If I can move and jump and run around and throw things, I have mechanical energy. I'm moving things. But we now know that light and sound and magnets and electricity, those are all also forms of energy. So I want to spend a few minutes here then actually discussing three different types of energy that, although they were on the slide we skipped here, I want to spend a few more minutes talking about each of them with their own slides. The first one is chemical energy. Okay? Chemical energy is maybe one that you haven't spent a lot of time discussing before, but if you mix chemicals, sometimes you can make energy. We've already discussed this in our chemistry unit. Do you guys remember the word exothermic reaction, the ones that give off heat? Okay. There are some things that require energy. There are some things that give off energy. Well, where does that energy come from? Well, it comes from the bonds inside compounds. As these chemical compounds have these bonds inside there, as we break them up in a chemical reaction, like for example, here's one, CH4 plus O2 makes CO2 plus water. It may also produce some energy. And the reason why it produces energy is that there are bonds in these chemicals, and there are bonds in these chemicals. And as you break up your reactants, remember that word? And make your products, the bonds will actually either give you or require energy by either being exo or endothermic. So that's one form of energy that we've already discussed a little bit. Here's another form of energy, and to me this one is actually one of the most important. I already kind of mentioned how I think electricity is one of the most important discoveries of humankind. There was a guy named Faraday, and we don't talk about him in this course here, but I spent a lot of time in my physics classes talking about him. He discovered a principle called electromagnetic induction. And basically the idea is, if you take a magnet and you put it inside a coil of wire, you can actually make electricity. And this is called the generator effect. I'm going to write that down here. Generator. And it's actually how we make our electricity. I'm going to show you guys this in a lab, in an activity next week, Monday, how we can actually create electricity. Because energy doesn't just come from nowhere. What ends up happening is you actually run a magnet inside a coil of wire back and forth and back and forth. And it actually makes electricity. It's called electromagnetic induction. And the words kind of make sense. Electricity, magnetic, magnets, induction. You can actually make electricity from magnets. And so this won't make sense to you just on a random slide in the middle of our notes, but I just want to point out that we're going to discuss this more later, the idea of how to make electricity. The last one I want to discuss is nuclear and solar energy. These are probably the two most common forms of energy that people would like to move us to. We often get a lot of our energy from fossil fuels, and we just finished our environmental chemistry unit discussing how there's a problem with fossil fuels. What does burning fossil fuels cause? Greenhouse gases. Yeah, which is contributing to our world becoming warmer, climate change, global warming. Right? Now, there's some debate as to what extent is happening, but most scientists are pretty much in agreement that yes, the Earth is getting warmer. They're not sure how much it's getting warmer or how bad it will become, but we would really like to get off of fossil fuels. That would be great. And these are the two most common ways that we're trying to get rid of that. One is through nuclear energy, where you can either split an atom apart, which is called fission, or fuse an atom together called fusion. And this is some pretty cool stuff, but again, we don't really talk about it much in grade 9. I'll talk about it more with you guys later individually if you want to know. But if you haven't heard these words, fission and fusion, these are the nuclear reactions, and they can give a lot of energy. But there's a downside: radiation. If you do it wrong, and you have a radioactive spill or some sort of meltdown, it can cause problems. There was one nuclear power plant in like Greater Russia. It was the Soviet Union at the time, called Chernobyl. Have you ever heard of Chernobyl before? It was a power plant in the USSR, and it melted down, and like it caused like an entire like massive area to become radioactive. To this day, like 30 years later, nothing will grow there, and you really shouldn't go there because there's still too much radiation that like you as a human, if you stay there too long, you're probably going to like radiation will cause the cells in your body to mutate, often causing cancer. So you have to be careful with nuclear energy. There are a lot of people who do not like the idea of nuclear energy. There are some who are like, we should invest all of our money into nuclear energy because if we can do it safely, we wouldn't have to worry about energy ever again. The last one is about solar energy. And we can actually get a lot of energy from the sun as well. And if we can harness solar energy, that's another good way of trying to power our world. There's a downside to that, though. One of the downsides to solar energy is the sun needs to be shining. And half of the day, it doesn't shine. So like at night, solar energy is kind of useless, which means you need to have batteries to store the energy. And then the other problem is that when it's cloudy out, like right now, solar energy wouldn't be useful. So like there is still some downsides, but those are the two most common forms of energy that we'd like to try to transition to. So, okay, I need to move on a little bit here. We talked about this slide. The next slide I want to discuss before we finally get to electricity some more is the idea that energy can be converted. So again, in the last 300 years, we've finally started to like narrow down what energy really is. It's still really hard to describe what energy even is, because they're so different. There's light and heat and sound and magnets and nuclear and solar and all that different stuff, right? What I need you to know, though, is that we can convert energy between forms. Let me give you some examples. A toaster. What does a toaster do? Well, it takes electricity and tries to give you thermal energy in the form of heat, because the heat is supposed to like crisp your toast up. Right? This device is a converter. But let me give you some more examples. What about a flashlight? Well, a flashlight takes chemical energy from what? Batteries. Yeah, batteries. And then it'll first make electricity, and then it will make light. But it's probably also going to make heat as well, because a flashlight will heat up over time a little bit too, right? But ideally, you want light. But there's like multiple different like conversions here, or a blender. What does a blender do? Well, it takes electricity and it makes mechanical. What was mechanical energy again? Moving stuff, motion, right? Isn't the point of a blender to basically grind things up in circles, right? Or a last one, how about a battery-operated clock, right? You have an alarm clock. What's the point of the clock? Well, batteries turn things into electricity. Now, that electricity causes motion. You know how like that clock at the back of the room there is like slowly but surely the little hand is ticking, right? So unless it's like a digital clock, if this is like an analog clock that like has a little thing rotate, it causes motion, and then eventually a trigger gets hit, causing sound, where the alarm goes, ring, wake up. So with all of that being said, that's the first half of my lesson. I wanted to spend about half an hour or so, 28 minutes, discussing all the different forms of energy. But now we want to very specifically spend the rest of our time talking about more or less just one form, electrical energy, which, as you guys can read here, we normally just call that electricity. But electricity is a form of energy. So we're going to spend the rest of my lesson and the rest of our unit discussing that. The first thing we want to discuss then is safety. Okay? That's a really important concept with electricity. You have to be careful around electricity. You can't just, if you have like exposed wires, you don't just go touching them because you can get electrocuted, right? Like most people know this, right? Like even my 4-year-old now knows not to stick a fork in a light socket, right? When we're little kids, sometimes we have those little like plastic plugs that you kind of put inside the sockets so the kids don't stick their finger in the wall. But like most of you guys know by now, be careful with electricity. Anybody have or seen one of these like boxes nearby their house? Like there's one that's like oh goodness, where's a good color here? There's one of these like 2 houses down from my house, one of these electrical boxes. You guys ever seen those before? You've probably been taught by somebody. If not, I'm going to tell you right now, don't play by these electrical boxes. Like there's actually a picture of like people getting electrocuted on them, right? So be careful by those. Let's talk a bit about why electricity is so dangerous then. Electricity always tries to find the shortest circuit it possibly can. What is electricity? Does anybody even know? What is electricity? Okay, I'll tell you. Electricity is the flow of electrons. That's actually where the word came from. Electricity is electrons moving. And if you have a lot of electrons moving, you have electricity. So what ends up happening, I'm going to try to make a new picture here, is that let's say that you were to have a battery. I'm going to try to draw this as like a battery right here. Here's like maybe the negative and positive ends of a battery. And then you have like a wire. And the wire hooks up to, let me draw a light bulb. This is a really crude light bulb here. We've now made what's known as a circuit, and really what's going through the wires is electrons. Electrons are going through the wires, kind of in a circuit. So that's what electricity is. It's a lot of electrons. Now, 1 or 2 electrons isn't a problem. When you have a lot of them, it can actually cause serious problems. One of the ways in which we measure electricity is a term called, it's capital A. Anybody know what capital A stands for? Oh, I thought I heard it. Amps. Well done. It stands for an amp. And it's a measure of electricity. And the long story short is that the more amps you have, the more electricity there is. But more specifically, the more electrons there are moving in those wires. If you have like a small little wire or like a bigger thick wire, you might even see sparks sometimes. Those sparks that you're seeing are electrons moving. Lightning, by the way, is actually electrical discharge. I have a couple of notes here. If you have like small amounts of amps, like these amounts here, it can actually cause loss of muscle control. We actually sometimes use small amounts of current to restart somebody's heart. You guys know that those electron defibrillators where you go clear, right? Yeah, defibrillators, right? You can actually cause, this is kind of crazy, if you've ever seen one of these before, find a YouTube video. Some people will actually take like frogs that are being dissected. The frogs are dead. And they will hook up a little bit of electricity to it and shock the frog. And the frog's legs will actually twitch, which is kind of cool. Also kind of weird. However, here's the important part. You can actually cause damage to your heart and electrical burns if you have even as much as 1/10 of an amp. Just 1/10 of an amp. Because what ends up happening is so many electrons go running through your body, it can actually cause your heart to burn. And all of a sudden, then it will stop working. So you have to be very, very, very careful about using too much electricity. Now, there's another word we use. It's called voltage. And voltage is measured in capital V. This is known as a voltage box. High voltage is also dangerous, but it's actually the amps that really is the important thing. They usually go hand in hand, but those are 2 things we're going to discuss later, amps and volts, as different ways of measuring electricity. So, okay, let's talk a little bit more about the theory behind how electricity works. There are some materials that are good at conducting electricity, and one of the reasons why is that they allow electrons to move through them. We already have a word that we've used before to describe things that can be used for electricity. Do you guys remember the word ductility? Ductility meant that you can make it into a wire, yeah. And so there are some things that are great at conducting electricity. Another word we use then is the word conductor. And the reason why is that conductors have electrons that are loose and able to flow. And those electrons are able to move very nicely. Metals do a good job of this. Well, the opposite of a conductor is called an insulator. Insulators don't let electrons move very well. And I've kind of got a picture going on here. This would be an example of an insulator. Can you guys see how the positive and negatives in these atoms right here, how they're kind of stuck together? Because these guys are so stuck together, this is an insulator, because electrons aren't going to move very nicely. This thing right here would be a conductor. Now, it's not conducting yet, but can you see how the positives and negatives are all kind of separated from each other. And in this example here, all of these electrons are free. They're free, they're not stuck. And the reason why that's important is that if voltage is applied, it can actually cause these electrons to all go in the same direction. And as soon as you have electrons all going in the same direction, we call that electricity. And it's the beginning of a circuit. Okay. Oh, why do I not have a picture nearby? Okay, I'm going to have to come back to this, I guess. Okay, can you guys find this picture over here? I know it's a little ways through our notes. But here's an example of a circuit, or electricity. Electrons are all flowing in the same direction. You probably live in a house. I don't want to presume that maybe some of you don't, but like if you live in a place with electricity, there's probably a transformer nearby, maybe outside on the street, but like somewhere nearby. Maybe you've seen these boxes on like electrical wires. Those are transformers. And what they're going to do is they're going to provide electricity to your house. And what ends up happening is electrons will begin to flow through one of the wires, see the arrow, and then they're going to go into your house. And you probably have like a power box somewhere inside your house, like a fuse box. That'll send electricity to different devices, but eventually it'll have to get returned back the other way to the transformer. Maybe you've never clued into this before, but here's a generic plug-in. Now, you know how some plug-ins have like 3 different wires to it, but some of them only have 2 different wires? Everything has at least 2 different prongs to it, because one of the prongs is for the electricity to go that way, and then the other prong is for it to come back again and complete the circuit. So you always have to have 2 prongs on something. Sometimes there's even the ground wire as well. I'll discuss the ground wire more in a bit. But that's kind of the idea behind a circuit, is that it's got to come in, go around through, it's got to link up, and then come back the other way. And if it does that, you now have electrons flowing in like a circuit, going in a continuous path. Let me come back to our notes here. So that's the idea of a conductor. This thing right here, once the electrons are free, they can begin to move, but they have to move like in a, ultimately like a circle. They have to come back on themselves to finish. Yeah, that's basically what this slide here discusses, is the word conductivity. There are some materials that are great at conducting electricity, but there are some materials that don't conduct electricity, which is really good, because we need those for our safety. For example, that plug that I had right there, I'm not going to go grab it again, but like any wire, the wire is a good conductor. But what's usually wrapped around the wire? Some sort of plastic or rubber coating, right? Like even just take your headphones you're wearing there, Zach, right? There's clearly wires inside the headphones, right? But around the outside of it, we put some sort of plastic. The reason why is that plastic is more of an insulator. Plastic doesn't let the electrons electrocute you, but the wire, oh my goodness, I can't even spell. Wire is a conductor. Okay. There are actually more than just insulators and conductors, though. Technically, there are things called semiconductors, which conduct sometimes, and sometimes not, hence the word semiconductors. And there's also things called superconductors, where they are so good at conducting electricity, there's almost no resistance whatsoever. So we're not really going to focus on these 2 things in this course. I just wanted to point out that there is more than just an insulator to a conductor. There's kind of a spectrum going on here. Here's a slide that kind of introduces some concepts, some pictures of things. You probably know a couple of these already. Like what sort of things like to conduct electricity? Metal, nails, tinfoil. Things like silver, copper, and aluminum are great at conducting electricity. Well, there are some things that suck at conducting electricity, but that's actually really good. Wood, rubber. Rubber is actually a horrible conductor, but it's a great insulator. It's one of the reasons why, if you are in a thunderstorm, one of the safest places for you to be is in your car. Because what is on the surface? What's on the outside of your? What does your car ride on? Tires is what we were going for. I didn't phrase that very well. But you guys know how like your car has tires on the bottom of them? Because your car has tires, electrons cannot go through your car. They would love to go into the metal. The metal on your car will totally take electrons. but the tires on your car will not let electrons pass through it. It's actually one of the reasons why, when we use insulators, big like rubber gloves like this are one of the safest things you can use. If you do have to touch electricity, you want these big insulated gloves because electrons can't go through them. Yeah, trees and wood and paper are also actually good insulators, as well as glass. The one that's not written on here, but we should probably add is plastic. Plastic is also often a really good insulator. We coat our wires in it. I have some slides here talking about some of the things I skipped over. So I need you guys to know the word conductor and insulator, but I want to talk about semiconductors a little bit, because that one throws kids off. So I'm not going to test you on this, but I want you to know what the heck a semiconductor is. A photocopier actually uses semiconductors, and hopefully this will make sense to you. Okay. Do you guys know how a photocopier works? Okay. You ever used a photocopier before? You know how there's that like little light that kind of scans along the bottom? It goes zzz, and then like stops, and like it takes like a little picture there. What that little bar is doing is it is shooting light through the bottom glass and trying to reach the top. And what ends up happening is light can sometimes go through things, but not through other things. Okay? Take a random sheet of paper and hold it up to the light. You can probably tell that like some light is making it through the paper, because like the whiteness of the paper allows things to shine through a little bit. Does that make sense? But what if there's ink on the paper? What if there is black ink on the paper? Will light go through the black part of the ink quite as well? Well, no. And so that's what the semiconductor does, is that they only conduct, specifically selenium is used, because selenium can conduct if light goes through it. So if light tries to go through the white paper, then the selenium works as a conductor, and then it reads a signal. But if the light tries to go through the ink portion, which is dark, light can't go through the ink portion quite as well. And so therefore selenium doesn't conduct as well, and a signal is not sent. Does that make sense at all? So that's why that little light runs along the bottom of the photocopier, is because selenium is being used as a semiconductor, and it will conduct if light makes it through, and it won't conduct if light doesn't make it through. So that's what makes it a semiconductor. Not because it's like halfway in between conducting, but because physical properties make it so that either it does conduct or it doesn't. It really operates as both, depending on whether there's light or not. So here's the last thing I want to, and then I'm going to stop talking about semiconductor because it's really not an important part of what we do. But I need you guys to know that semiconductors are a big part of the computer electronics industry, because we need a lot of our devices to sometimes send a signal and sometimes not, and then later change, right? And so we actually use a lot of semiconductors of selenium, silicon, germanium, and carbon. We often use them a lot to make transistors. You guys ever heard that word before? Or like computer chips are often made with these. Okay. Last topic here that I need to move on. There's actually things called superconductors. These are kind of cool. They are so, I want to use the terminology I wrote here. They are so fantastic at transferring electricity, they lose no energy whatsoever. I need to discuss this for a little bit here. Let's say that you have wires in your house that are conducting electricities. And maybe you overload a circuit with too many devices. You ever had like the fuse trip in your house and you have to like go reset it? You ever seen one of those things before? Because one of the problems that can occur is that when electrons are moving, they can move so fast, it can actually cause heat. And heat can cause friction, which can eventually cause like a fire. And electrical fires are a very, very big problem that we want to try to avoid. So normally what we do to avoid electrical fires is we add resistance. We try to prevent the electrons from going too fast, because if they run out of control, it can cause an electrical fire. Okay? Well, what's cool about superconductors is that they are so fantastic at transferring electricity, they don't lose any energy due to friction whatsoever. They're almost in a frictionless environment. But it also then requires almost absolute zero, like the super coldest temperatures possible, like say minus 200 degrees Celsius. So although it would be really cool to like have all of our electronics run at minus 200 Celsius, because it would really prevent electrical fires, it's not really realistic, but it's kind of a cool property. So there is a spectrum then. You have your conductors which conduct electricity and your insulators which don't. Your semiconductors which conduct but only under the right conditions. And you've got your superconductors that not only do they conduct, but the electrons have almost no resistance due to friction, and like these wouldn't even cause an electrical fire. But they require like absolute zero temperatures, like minus 200 Celsius to work, so. Okay, I need to almost finish my notes. What do I got left here? Okay, we're almost done. I've got 20 minutes. Here's a slide where I want to talk then a bit about more of the safety issue. We need to prevent electrical shocks. And so we often use insulators like these rubber gloves right here. But there's another way that we try to prevent electrical shocks. Remember how I pulled out the one plug right there and talked about it for a second? There are always at least 2 parts to a plug-in, and sometimes there's the third one. Okay. The 2 plugs right here, the 2 main ones, the words we use are the neutral and hot wire. And this is kind of a little bit of like electrical engineering. The way it works is that you have a hot wire. And the hot wire is the wire that carries the electricity to your device. So like you have a main electrical panel in your house, and electricity is going to come to the outlet. Then you're going to plug something into the outlet, and electricity is going to go through the outlet to a device and then back again. Well, then the electricity needs to go back to the panel again. We call this one the neutral wire. There's actually still electrons flowing through it, but not nearly as fast as the hot wire. Because the hot wire, the electrons are just firing through here, right? Then they go through a device, and then they kind of get slowed down a little bit because the electrons lose their energy. They still have some energy, but they've like used their energy up to run your device. But then they need to go back to where they start so they can get looped back around again. Okay? So that's basically the 2-wire system. Well, there's often a third wire called the ground wire. And I want to go to this picture here to describe a ground wire. So imagine you have this scenario again here where you're a person, and as a person, you happen to be not very careful, and you are like really near and touching exposed electrical wires. Well, here's what happens. Outside of your house is that transformer, right? And it's providing electricity, right? Electricity is coming in through this wire right here, which we now know as the hot wire. And ideally, the hot wire should then return the electricity back through the neutral wire, and there should be a circuit right here that goes. However, electricity always wants to try to find the shortest path it can. And so electricity, the electrons, they need to get back to here. What could actually end up happening, unfortunately, is let's say that it's supposed to go back through this neutral wire here. That's the way it's intended to go. But you touched an exposed wire. Electricity could go through you, through the ground, and back up to the transformer. And it could make a circuit that goes like this. And this is really dangerous now, because what's happening? Well, electricity is going through you. Most specifically, it's going to run across your heart. And as we know, the defibrillator can get your heart started again, but it could also stop your heart. It could also make it run too fast. It could even just cause a burn and cause the muscles in your heart to become weakened. So we don't want electricity to ever accidentally go through a person, which is why we have this third little plug on the bottom here. We call it a ground wire. And here's a second picture describing what it's supposed to do. It's the exact same picture, but it's got an extra little bit to it. So again, the electricity is supposed to go through the transformer, through the hot wire, and then back again through the neutral wire. And it's supposed to go through this circuit right here. But let's say that somehow you get an electrical shock. Well, what's going to happen is rather than the electricity going through you, it's supposed to go through that third plug in the wire. And that third plug in the wire will then take it to the ground and do a loop instead. And what's going to happen is it's going to bypass a person. Let's compare 2 things. Let's compare a person to a wire. Can electricity go through a person? Yeah, totally it can. But is it as easy compared to a wire? No. Because a wire is a very good conductor. A person is kind of a in-between conductor. Not a semiconductor, though. Because a semiconductor means you only conduct like under the right conditions. Okay? So if electricity has to go through a wire or through a person, it will go through the wire, which is why we use that ground wire to protect you, so that rather than the electrons going through you and then into the ground, It goes through that wire. So it's actually very important. If you have one of those plugins that has like the third little circular one, never cut that one off to try to like make it fit a plug. You need that wire because that device probably uses enough electricity that if there was a short circuit, it probably has enough that it could actually cause like to electrocute you. We want to avoid that, obviously. Does that make sense? Okay. A few more things, then we're done. Lightning is actually a form of electricity, only it's a lot of electricity. It actually has as many as 30,000 amps. How many amps did you need to kill a person? Yeah, 1/10 of an amp was enough to cause like problems in a human. Not many people survive lightning strikes. It's possible, it's happened, but that's pretty rare. Usually it causes some pretty major damage to your muscles, especially your heart, because of how much electricity has all of a sudden run across in a short period of time. So most of the time, lightning is lethal. I want to talk about some things that structures have to try to prevent lightning strikes from being so damaged. It's called a lightning rod. And I've got a couple of pictures here of lightning rods. For example, a building. A building, even like this one right here, probably has a built-in lightning rod where there's like a little antenna on the top of the building so that like if lightning strikes, it's probably going to hit the lightning rod, and then it goes through a wire outside the building through the ground. Therefore, all of the kids who are inside learning about electricity, if lightning were to hit the building, we're nice and safe. Here's a picture of a barn I found. It's got the exact same thing. There's a couple of little wires up on the top here, a couple of little like antenna, so that if lightning hits the building, it'll hit the antenna, go through the wire, and go to the ground safely. Otherwise, if you don't have a lightning rod, lightning could strike this building and it could light on fire. Oh, good question. So lightning is caused by a static buildup in clouds, where basically electrons in the cloud end up building up on the bottom side of the cloud. So what you end up having is a cloud. Let's see if I can draw one. Here's a cloud. Okay. And what ends up happening is all of the electrons in the cloud, I'm going to use negatives to describe electrons, all end up on the bottom side of a cloud. Okay. And what ends up happening is there's so many electrons here that they just have to escape. And the way in which they escape is by causing a lightning bolt to hit the earth on the ground, and then all of the electrons can kind of like rush out of it. So then the bigger question is, well, then why do all of the electrons build up on the underside of the cloud? And then there's a lot of different factors to that. Like that's like what a storm is going to cause. So, but like at its core, it's due to so many electrons being built up in one spot. They just have to like escape. Okay, I'm almost done. Thank you guys, by the way, for staying with me, because this is a long lesson. There's a lot of me talking today. I need you guys to be aware for safety concerns that water and electricity do not mix. You should be very careful not to have the two things nearby. Like there's some people who maybe bring their cell phone into the bathtub or other electrical devices. You really shouldn't. Not because you could ruin your cell phone, but if electricity gets into water, it can actually cause the circuit to go through the water and through you. And so we want to be really careful about that. Now, I need you to know this, though. Pure water actually does not conduct electricity. If you have 100% pure water, it is actually an insulator, which is really weird. However, most of the water that we have is not pure. Most of the water we have has like dissolved ions in it, like little bits of sodium or nitrates, and like in small amounts, it's fine. Okay. Anybody ever buy like a bottle of water from the store? And like if you read the label on the water, it'll talk about how there's like parts per million. Oh yeah, you have one here. Can I borrow yours? Is that a bottle of water there? Can I borrow it real quick? I see. Does it say on the side there, parts per million? Yeah, it does. Okay, so you look at yours later again here. If you look at the bottom here, it's going to talk about how in parts per million there's different things in here. There's 5 potassium, 18 calcium, 9 chlorides, and 18 sodiums. If you guys ever see a water bottle like that, look on the side for where it mentions some of the little dissolved things. It'll probably be in ppm, but we've already learned ppm stands for parts per million, right? So there's trace, very small amounts of ions in water. And because of those ions in water, those dissolved ions, water actually then will conduct electricity very well. So unless it's 100% pure water, if there's even anything dissolved in it, water conducts electricity so well that it could cause you to become electrocuted. So long story short, like, do not take your electric hair dryer and bring it near a bathtub, because like that's how you can get electrocuted very easily. Last thing we're going to talk about, some safety mechanisms to prevent electrocution. I've got two that I need you to know. I almost guarantee you this is going to be on the PAT. Near guarantee. I can't make that 100% promise, but chances are there's going to be at least a question about this. One of them is called a fuse. A fuse is a tool that we use to protect against things getting too hot. Okay? Again, what is electricity? Well, it's a bunch of electrons moving. And as those electrons race faster and faster and faster, friction occurs, and they can heat up. And for safety's sake, things might have one of these inside of them. These are fuses. Okay? Can you guys see how this right here, there's a small little strip of metal through the middle here? That strip of metal can continue conducting electricity. But if it gets too hot, it will melt. And here is a fuse that is melted. And it's a safety precaution so that it doesn't start a fire. And so this little piece of metal will then melt, it'll break the circuit, and then the whole thing will shut off. Which is really annoying because then you have to go replace the fuse, but at least you didn't cause an electrical fire. This thing right here is often known as a fuse box or a circuit breaker. And it works. You guys ever seen one of these in your house? Every house should have one, right? What ends up happening in the fuse box is a very similar thing. If too much electricity is running through it, and it's at risk of starting an electrical fire, one of these little breaker things will trip and it'll flip itself off, basically. And that's a safety mechanism so that it does not get too hot. Because if it gets too hot, it could start a... There we go, yeah. Okay, my last slide right here is just some safety pointers, which you guys can read later. You probably know these things, like stay away from power lines, don't use a power cord that is broken or frayed, don't put anything into electrical outlets other than proper plugs. You know, things that I teach my 4-year-old. So, okay, let me summarize, and then you guys can take off here if you'd like. This was a long lesson, so thanks for staying with me. I think there were probably 2 halves to my lesson. The first half of our lesson was all about what is energy. And hopefully you have a slightly better idea of what energy is. But if I asked you to define energy, if you still struggled with that, that'd be fine. Because energy is hard to describe. You've got light and sound and heat and mechanical, and they're all so different. But at the end of the day, the one thing they all have in common is energy lets you do work. You can do something if you have energy. If you have mechanical energy, you can run. If you have light energy, you can see. If you have sound energy, you can hear, right? So like you need these energies to do stuff. So that was the first half of our lesson. The second half of our lesson, we discussed what electricity is. And the basic idea behind electricity is it's a whole bunch of moving electrons running through wires. Now, the wires have to make a complete circuit, a full loop. You guys with me still? I'm almost done, I promise. If you were to break the circuit, break the loop, it stops because it has to go all the way around in a full circle. A couple of ways that we protect against that is fuses and circuit boxes, because if they get too hot, it'll melt a small little section of it, and then that stops the circuit from flowing, because electrical fires are a real possibility. Okay. We also want to protect people against electricity going through humans. It's very, very bad for your muscles, specifically your heart. Okay. And so that's why we have safety features like that third ground wire to make it so that electricity goes through the ground, through that ground wire, and not through you. Okay? We can use electricity to restart somebody's heart, but we got to be careful about that too, right? Like, you ever see like medical shows where they do like, set it to 200, clear, and they zap them. And then that doesn't work, right? Set it to 250, clear, zap them, right? They always have to work their way up in little increments. You do that too many times though, and you can fry somebody's heart. So you do got to be careful, right? But if their heart's not beating, you kind of need to get it beating again though, right? So you do what you can to get it going again. So that's more or less my lesson. Hopefully at the end of today, you should know a bit about insulators. Lara, guys, stay focused, please. I'm almost done. You should know about insulators. You should know about conductors. Maybe even you now know a bit about semiconductors. But like, don't stress over that. That's not really the point of the course. Tomorrow then, we're going to start talking about some of the math formulas that are attached to this. So you need to bring along something that can do calculations. Your cell phone's fine, but if you can, maybe bring a calculator along, and we're going to start doing some math formulas and doing some calculations on this. So, does that make sense? Okay, thank you guys for staying with me for 60 minutes. That was a long lesson. If you guys would like to, you're free to go.